I forgot to do that. Okay, so now we're recording, and so I'll talk about the um, SCC 21, and I've given you the updates. So the student cluster competition, we talked about this in the first week. This has been around since 2007. Hundreds of students around the world compete. The year I've done 3 now, and each time there's been 16 to 18, 19 teams. The teams are limited to 6 students on the active team, but you have mentors and teachers and faculty involved in. For our programs, the ones I run, I always bring in extra mentors so more students can learn. But the 6 students come and they end up working in a tiny little 10 by 10 foot booth. You have to cram the students, the equipment, the rack with your computer on it, and you're on the floor out with a few hundred other students. It's quite exciting. It's a competition that runs for 48 hours. When this was in person, the virtual one ran for several days and the rules were a little bit different. But nonetheless, it was very exciting to get out there and you see what the other teams are doing and you try and match what they're doing. Quite exciting. And the goals are to learn to operate and maintain a cluster. It's one thing to use a cluster, but when you actually are in the same room with that rack of equipment running and you hear it go to work when you're doing a real large scale computation, you literally hear the fans turn on. And if you think your laptop makes noise when a rack of 10 nodes fires up, it's just deafening, and the breeze come from the fans. It's quite exciting, but also you learn to handle it when the system goes down. You learn to install all the software and maintain the software and tune the hardware and the software so they work better together. You learn to run and test science applications. And then there's this new program called the Reproducibility Challenge. If you're in physics or any hard science, biology, wet lab work, you have to be able to reproduce your results to within some important statistical variation. If I put a paper out and I'm working in optical physics and I claim to see some behavior based on the laser light I'm using and the sample size I'm working on, somebody else better be able to reproduce that, or I haven't given them enough information, or I've made a mistake. So reproducibility in science is essential. A few years ago, the supercomputing community said we don't have that in computer science and we don't have that in computational science. So they began this program called the reproducibility effort. And the goal is over time to learn what does somebody need to put into the artifacts associated with the paper you're publishing in order for somebody else to reproduce your work. There's 7 ways to write a do loop. They should all get the same answer. And there's many ways to do computational science. And so what are the artifacts, the material that you need to provide in order for your work to be reproduced? And starting in 2016, they started asking the students at the student cluster competition, one of the challenges is they give you a paper from the year before, and everybody has to try to reproduce the results of that paper on the hardware that they brought, because computers are heterogeneous. They're never all the same. And even if you build a system where you buy all the same Intel processor, every year that new version of that same Intel processor will be a little bit different. So things can affect outcomes. And the goal is not to get the right answer in the sense of exactly what they got. The question is to get close. And if you got close, how did you do that and why? And if you couldn't get close to reproducing it, what were the roadblocks and why you found this? Because the first year I went, we actually had a system that didn't reproduce the right results, and we figured out why and had to make a change to the system, and we got close, and we ended up being part of a series of papers published on that. So you might not be able to because your system is not a system where the application performs well. Okay, so it's a very exciting thing to be a part of, and we've been selected this year to contribute to the IEEE journal computing on this challenge. And then there's something called the power outage. In real life, the power can go out at any time. So what happens when the power goes out? And you have to be able to restart your system, rerun your code if you need to, know where you were in your code. So these are all really interesting challenges. And so today we'll talk about our plans to make a team. To compete, there's these 6 undergraduates. We're going to be opening up the student team application, online application form. And you need to think about the fact that if it's in person, and if we choose, this year there might be an option to be virtual or in person. You would travel to, this year it's St. Louis, it moves around the country. And everything's paid for, though, for you. All travel and expenses are paid by the Student Cluster Competition Committee and SDSC. We get vendors to help, but you don't have to pay for anything except maybe if you want some Starbucks or your own lunch that we're not hosting. And then it does require a significant level of commitment. And this year, I'm pleased to announce we're working with Brian Chin in the CSC department, and we'll be able to get 199 credit for the team, the core team, and also our additional participants that we'll be bringing in as alternates, so to speak. So it's a pretty interesting time. So today, I'm going to wrap this up real quick, but I'll put this into the chat. This is the link to the registration form. I'll show it to you in a second. And we do have a timeline. It's pretty tight now. Proposals for a team are due May 3rd. And for that, we need to figure out our hardware. We're working on that already. We need to pick our team based on your applications. And we need to get a section written about the team. And so the application deadline is Friday, April 23rd. It's a pretty simple application, but be sure to put in there the information about you, that about why you want to do it, and what you know that might apply, even if it's not parallel computing. You might know some things to help us do better. Excuse me. And the application notification will let you know right away on Tuesday and on the 27th, and then you have to tell us that you're going to accept and participate. It's not a trivial decision. So we appreciate that some people might change their mind. And so we need to know by Friday, April 30th, in case we have to invite an alternate. And then if selected, we start learning the programs and start studying hardware, working with the Supercomputing Club. Whether you get on the team or not, you're welcome to join in the fun of learning about high performance computing. Okay, so we had Team Superscalar. They placed 4th overall out of 19 teams from around the world. That's pretty good. So they've raised the bar pretty high, folks. But let's see what we can do. Jacob will talk to you about the team. I just wanted to go to this final dashboard of information, where for the first time they had a Grafana dashboard, and it listed all of the teams and the different applications, like the reproducibility challenge, and then some benchmarking challenges, which I think you'll hear about today from the students. And it shows whether people got it done or not. And then over here, it does give the benchmarking numbers. And that was really exciting. There's nothing like knowing who's the best, who's beaten me, and what do I have to do to catch up with them. And so instead of being sort of like, well, we're not as good, what I found was the team attitude was amazing. They just said, well, we can do better than that. And they would sit down and strategize. So getting that feedback of seeing what the other teams are doing, it's really a positive experience and adds to the fun and the excitement, especially when it's virtual. So with that, we do have quite a few sponsors. Some of them you know, and some of them you don't. But these are the companies that either lend us hardware like AMD and NVIDIA, or let us on their systems like Microsoft Azure and Amazon Web Services, or and then big research organizations that fund the projects at SDSC, and this is how SDSC can afford to sponsor this activity. With that, if you have any questions, feel free to ask me. And if not, there's a link in the chat, but I don't know if it shows for everybody, so I'll repost it. And Jacob, I'll stop sharing and turn it over to you. Oh, I was going to show you guys this is the application. There's a couple sections to it. Okay, and it's self-described, and I hope to hear from a lot of you soon. Thanks. Jacob, it's all yours.
Okay. Hi, everyone. But Mary, probably Joey want to go first because he got something to do at 1:45. Joey, are you here?
Oh, that's fine. It's up to you.
Yeah.
Yeah, I'm here.
Okay.
You guys hear me?
Yeah.
Okay, so I will be talking about how to build a monitor to monitor the Azure Cycle Cloud. So yeah, this one. So most of the time we can just use Grafana to monitor the thing, but if we want to like maybe more personalize the monitoring thing, and maybe we can like instead of tracking one big machine, we can track each of the compute nodes that's on our machines. We would probably have to build our own personalized monitor. And it's pretty easy to actually build a monitor for the Cycle Cloud because Cycle Cloud has a command that can show every information on the machine, including the cost of per time, and including what machine are we running on, and including I think we also include the power that attached to the machine, and we include almost everything. So the best way to do it is like we first run the command, and we scrape all the important data on the command, including something like the cost per time units, and including what machine are we running on, and also including how many time are we running on. We can really simply can build a data around it. So we're first scraping the data, and then we can use a simple JavaScript to actually convert it to a really good graph, and then we can use the GitHub website to actually host it. I can actually show you guys the website.
You need to share screen.
Yes, give me one second. Can you guys see my screen? Can you guys see my screen?
Yes.
Okay. So as you can see, we can see the price per hours within one graphs, and we can see the jobs that we're running on. We can see Jacob is running the MEMX CT, and someone is running the GrowMax, and someone is running the HPCG, and we can see the total cost over the time, so we can better keep track of the thing. And this graph is simply just using a JavaScript, which is yeah. So we can see this graph as the results of the data we're just scraping from the Cycle Cloud command. And to better use of this code, we can just host it on a Raspberry Pi, and then we can just use a cron tab to make it run every, say, 5 minutes or 3 minutes. So as long as the Cycle Cloud machine is running, we can see this graph. Yeah, that's it. Thank you.
So Joey, why was it important to develop that script?
Oh yes. So so in the SDSC competition, we actually have a limit of the allocation. I think in SDSC 20 the allocation limit is $3,000, right? Correct?
Mm-hmm. Yes.
Yes. So to better arrange all the jobs that we run and all the process that we run, we better keep track of the costs right now, so we don't running out of the money before the competition ends.
So thanks, Joey. So I'll share my screen for a moment before Jacob. I wanted to point out to folks that if you can see this, this is the Azure Portal. You log in and you manage things, resources and services and accounting and groups and stuff like that. But for the student cluster competition, we were invited to use this other tool called Cycle Cloud. And on it, you can build and define your own virtual machines. And there's a scripting client that goes to, Azure has a scripting client for all of their tools and services. So you can get on the command line and run things. So this one here shows that we're running Max Apodaca's IO 500 benchmark, and it tells us when it started, what's happening, our cores and nodes ramping up or not, and you get some messages and you can see, you know, it's beginning to do some work. The problem is that Amazon and Azure, they have these huge latencies in telling you how much you've actually spent. Like you might find out 3 days later, and that happened to us. One day we came to work before the competition, and you know, $1,000 had been spent, and we just didn't know that. And so during the competition, because we needed to know the budget literally minute by minute, we started developing tools, and one of them is the tool that Joey showed you. We had another tool that we put together. Where'd it go? There you can see some, I'm trying to find, that's right, we made our own spreadsheet so we could look at the hourly spend drew by each of the different applications, because we'd have to know how, as we ran out of money, how much work could we do? And could we keep competing at higher and higher levels? It was a very interesting way. So Joey came up with this idea for his particular script that could grab the information using a command line Azure Client API. So it was very clever. Okay, so Jacob, I'll turn it over to you again.
Sure. Just give me a second. Let me first continue on talking a little bit about the monitoring stuff, because you can see this application usage sheet is actually like a collection of times versus the machine we're using. So basically, when you want to start to run your application, you manually fill in the blocks. For example, if for the first day, if I want to run GrowMax, the GPU version, at let's see, at like 5:40 p.m., then you all have to fill in the number of machine you're using, and then the graph will change accordingly. Basically, you'll see because there's another restriction. There's a public ID restriction, IP restriction, so we can actually have more than, can remember, like 7 machines working together, or we'll be punished for violating the rules. So Max, who is another co-lead, is very, very strict on us. He actually, yeah. So basically, if he finds us using a machine without filling the form, he's gonna be mad. Yeah, that's a fine.
Yeah, that's a good point.
Yeah. So let me.
And although this looks like it might be, well, it's just the competition. It's interesting to point out that how many different machines, you don't have one virtual machine that you set up and then run all your applications on it. What the students chose to do was to create different virtual machines and different architectures of the virtual machines and different software installations of each of those virtual machines. If you go back up to the top, Jacob, there you go, on application on the left, each one of those applications from lines 2 to 12, each one of those was a different virtual machine that the students learned how to build out and then use SPAC to install the software. It was really highly developed, and then tracking how much they cost, and somebody kind of forgetting to turn off the machine and it would cost more money. And this is real life. This is how it's really going to go for you when you're out there working on the cloud. Clouds are promoted as well. They're really straightforward, but they can be pretty complex. Okay, thanks, Jacob.
Yeah, no problem. And I'll start again with the slides. Okay, so this is a slide we used for lightning talk during the competition, and I've changed it a little bit. So let me start by presenting it. So everyone, can you see my screen? Can you see the slide?
Yes.
Okay.
Yeah, I can see it. Thank you.
Thank you. So basically, I'm going to talk about a little bit about the competition itself, and about 1:45, see how it's going to come in and talk about Romex, and then I'll probably talk more about Memexity. So before that, I'll give you a brief introduction about the competition and the introduction about our team and our needed. Okay. So who are we? I'm Jacob Lee, and I'm currently a third year computer science major and math minor, and I was one of the co-lead of the team. And the main job I did during the competition was helping Max to uh, do some cloud administration stuff, and also I was the main person to handle the Memexity. And other teammates were not here today, but I'll do introduction. So Max is the other co-lead, and he's the one who's in charge of the timesheet, the usage sheet I just mentioned. And he was working on the IO 500 benchmark, and he completed it in the first day. So all the benchmark people, I'll introduce them later, were doing the mystery application, which we didn't know until the start of the competition, called Minibite. So let's keep going. So Arnav Gupta, he was in charge of HPCG, which stands for High Performance Conjugate Gradient, which is a benchmark. I'll introduce it later. And yeah, let's see. Zihao Kong, he's in charge of GrowMax, and he is going to introduce GrowMax in 15 minutes. Hong Yipan, he was in charge of the CESM, which is a modeling system for modeling and prediction system for global weather. And it's a very strong application. You can actually, given enough time, you can actually predict the weather of Earth 100 years later, like that. Let's see, Hong Yu Zhou, he was in charge of HPL, the high performance LeanPack benchmark, and all of them, but Zihao won't be here today, but I'll do my best to cover some information about their application and also mine. So what is the job we are trying to do? So before the competition, we don't really have a clue. And after, so basically we are going to build the most performant cluster in Azure, which is a cloud platform, for 7 different applications. So it turns out building the most performant cluster with a $204,000 budget. It turns out that building one performant cluster is not the best choice to do this because it's gonna cost a lot when we turn it on. So we decided to make 7 different, 7 customized cluster for each application. So in this case, we can actually turn it on once one of the application is over. So these are the 6 known applications. I use the word known because the 7th one, the mystery application, we didn't know it until the competition starts. So the first 3, the HPL, the IO 500, HPCG, are the benchmarks. And this benchmarks for HPL, we are actually solving a very dense matrix system, and it's quite computation bound. So we really want some machine that is, say, really fast in communication and also computation. And it's not taking a lot of memory. so we decide to use the HB120 series, which is the machine with the AMD EPYC processor. It's pretty fast. I believe the others, other school who achieve higher scores, turns out they're using GPUs, and we found out we realized it was a better that was a better choice after the competition. And for IO 500, it's a benchmark to test out the throughput and latency of your file system. Basically, you can choose some open source file system. For example, we use BGFS, which stands for BG file system. And we did pretty good on IO 500, but there were other schools who use some not open source software, probably from their lab or some other company who sponsored them, and achieved amazingly high score. For example, I believe our score on on IO 500 was 16, and Tsinghua University from China, they achieved the score of 300. So basically, like a lot more higher than us. And for HPCG, which stands for High Performance Conjugate Gradient, it's a similar task compared to HPL, but the difference is HPL is solving a dense matrix system, while HPCG it's a more sparse matrix multiplication system. So a potential problem is that it's actually taking more space than you think, because there are a lot of zero entries in the matrix. So besides the computation, you also need to set up other configuration that helps this sparse matrix multiplication, like help to speed up the process. And I'll actually cover those strategies and when I'm talking about MEMXCP, because MEMXCP is also solving a sparse matrix multiplication system, and we'll see how we solve it. Okay, let's talk about our cloud setup. So basically, you can see that we are using a cloud platform called CycleCloud, right? And the CycleCloud the CycleCloud platform allows us to create whatever machine we want, virtual machine we want. So basically, our setup is like, this is our initial salt. We have a admin node or the login node. If you are familiar with Comet or Expanse, you know that there are compute node and login node. So we call it admin node, where we have a very cheap machine on the admin node with Slurm build and BGFS head. So for the compute node part, we have a ND40s 40RS, which is the GPU nodes, and HB120RS are the CPU nodes. So it's similar to Expanse or Comet. It's like compute and compute GPU, stuff like that. And all of these nodes are connected through InfiniBand network. And for IO 500 benchmark, like itself, we have a different setup for all compute node. They're also connected with BGFS, but we realize that it's not easy to have like 7 very different setup scripts prepared for 7 different applications. So we choose another unified approach, which is we have the same admin node, but for the compute node, we either have GPU nodes or CPU nodes, because we don't really need both at the same time when we are running different version of code. For example, for GrowMax, there are GPU code. We don't really need the CPU at the same time. So we can actually have a GPU only cluster, and we can turn the CPU one down once we're not using it, once we're running the GPU one. Okay, and every single node inside the compute node portion are connected with InfiniBand and weaponed with BGFS. So for a CPU instance, I've been calling it HB120RS. It's like stands for I can't remember, but 120 stands for the 120 CPUs. So if you're familiar with AMD EPYC structure, EPYC processor, a very strange thing is EPYC processor got 64 CPUs or 64 cores, but on our machine there's only 60 CPUs. The reason for that is the Cycle Cloud organization hold back the other four so that they have a better control, or they can. I'm not exactly sure, but they probably hold back the four for security reason. And so in total we have 60 plus 60, that's 120 cores. And the reason we choose it is that it has a very big RAM, 480 gigabytes, and there's no GPU, and interconnect can be connected with InfiniBand, and enough disk, and a decent cost. For the GPU instance, for the GPU instance, we choose the ND series, not necessarily ND40s, because ND40 is extremely expensive. For one machine, which have, I can't remember, like four or eight GPUs. 8V100 GPUs. It costs like $26. So we probably use the ND24. And there's actually a limit on ND40 series, because a lot of other schools were trying to use all their budget on benchmark by using ND40s, like 10 ND40. But that's not allowed during the competition. And yeah, you can see it's with 8 Tesla V100 GPU. And the software tools we used are going to be introduced. So we use Cycle Cloud templates. This is for the very primitive setup for the cluster. As you can see, we basically have the Slurm setup and the BGF. So let me see. So you can see the Slurm auto scale is true. We're basically setting up the Slur, and we are setting up the BGFS head. So all of these cloud templates were done by Max Apodaca. He's very good at this. Without him, we are not going to do this easily. And chef recipe is more like your bash RC in your server. So this chef recipe is it's the next step after executing the cloud Cycle Cloud template. It's for initialize the BGFS. And for some application, for example, CSM, we use spec. Because spec, for example, if you want to install a compiler, let's say GCC, you can do spec install GCC, and spec will resolve every conflict or dependencies that's on your computer, and it can build whatever you want for your computer. And the other very good reason we use spec is that in the very earlier stage when we were we were doing training on Comet, we don't really have the sudo right, the super user right to change a lot of binary files. But spec actually create a Docker-like environment. Every time if you want to use your own environment, you can do a spec load the application, something like that. And let's see. Yeah, so for application, I'm not going to talk about the MemXCP yet because I believe Zihao is here. Let's have a look at here. Zihao, can you hear me?
Yes, I'm here.
Okay, great. So I'll hand it to you, and once you're down, I'll keep talking about MemXCP.
Okay, do you have some slide for me, or I will just talk about stuff?
Sure, I can use my slides, but it's not a lot of.
Yeah, it's fine. Okay, so okay. Yeah, so during the competition, every one of our teammates get assigned to one specific applications or benchmark for to do. So I was the one that does this GROMACS challenge. So the way I did it was that like during the train like before the competition, I know this, and I know I'm going to use GROMACS to do the competition. So I just sort of practice installing this with a bunch of dependency. So that takes me like I think it's like 3 weeks to figure out what is the best installation like process on our AMD EPYC machine. So for example, if you want to install GROMACS, there are a lot of options. You can, for some computer, for some CPU, it has some several instruction set. For example, AVX2, AVX256, AVX512. So there are some options that you can toggle. If you got like a processor which only has AVX256, then in order to install GROMACS, you need to turn that flag on. But like for our machine, which has AVX512, I turn that option on. And then there are also some dependency libraries, for example, fast Fourier transform libraries. And also there are certain compiler constraints for installing GROMACS as well. So actually figuring out what's the best way, actually there are GPU support as well. So figuring out how to install GROMACS that best fits our system takes 3 weeks of practice. Actually not practice, but like figuring things out. And after I install this correctly, it's still during the training process, during the preparing for competition, I just run some of the benchmarks using GROMACS. Like I downloaded some benchmark online, for example, like some molecule files that I want to use this GROMACS for. So the GROMACS will give you a sort of like a performance report. For example, how long does it gonna take for you to run this benchmark? The shorter it's better. So during the last like few weeks of the training process, I was just trying out using one benchmark. How do I get this faster? I need to sort of figuring out what is the performance bottleneck for one specific benchmark. For example, for that specific benchmark, one of the forces calculation takes 50% of the time. So if that forces can be, if that kind of computation can happen on GPU, then I can sort of offload that using some of the special command in the GROMACS. So during the last like 2 or 3 weeks, I was just figuring this out and then also preparing for competition, because during the competition, all of the input files and all of the experiment that I was going to run are unknown. So in order to like best prepare for the competition, I just gonna do like all of these sort of simulate what I'm going to get on the competition by myself. So, in that way, I sort of prepare what I like. If the competition asks me to do A, and I already prepare how to do it, like I already like figure out how to do A by myself in my training time, then I'm gonna save a lot of time during the competition. So that's sort of how I prepare, and then how did I use that's sort of the experiences of how did I prepare for the competition, and how did I perform on the competition. And then the result is actually for the specific application for GROMACS, my point is like the overall number 2 across all of the different teams. So I think I was kind of, I still feel kind of good about it, because I did a ton of time preparing this, and I got a good scores. Yeah, so I was able to contribute to the point, to our overall scores by a lot. Yeah.
Shihao, can you talk about how the real use cases that they gave you during the competition,
Okay.
and how challenging those were, and also how did it feel to wonder, oh, am I doing good enough when it was so hard to finish a run?
Yeah, I think the real use case is that I think the competition committee gives us a sort of a bunch of proteins related to like COVID-19. I don't really know the chemistry or the biology behind this, but I was just given a bunch of different proteins, and then the GROMACS can do some simulation with this protein. For example, put this protein in some solvent, and then sort of inspect how it will interact with the molecule that is around, that is in the solvent, and then calculate some forces, like maybe EM forces and some, other stuff that I'm a computer science major, so I don't really know, but like I was just following. I was given a very detailed experiment to run on this GROMACS. I think that experiment is for every applicant, for every candidate, you need to figure out what does the term mean, because the experiment is quite domain specific. So I need to know, what does the blah, blah, blah force mean? What is that? Calculate X, some blah, blah energy or potential energy. What does that mean? So that was sort of kind of challenging, because during my training process, I only download benchmark data, run the benchmark data. I wasn't really prepared for like those scientific terms and scientific, lab reports. So that one took me a lot of time. And then also the experiment that the committee gives us takes a lot of times. Like maybe one protein file, you need to run like 30 minutes in order to get the result. And then in order for the data to be consistent, you need to take multiple trials. Like you need to take multiple runs for the same protein. So that means if I have 4 proteins and each protein I need to take 5 different samples, I'm gonna get 20 different runs, and each takes like 20 or 30 minutes. So that is like a lot of machine times. So I still remember during the last few days during the last day of the competition, since we are sort of running, like we decided to run all other applications first and then see how much money we left. So for example, we left $500, and then I'm gonna use this $500 to get as much as possible, so that gives us totally more points. That's sort of our strategy. But like in general, this GROMACS experiment takes a big amount of time.
Yeah. And actually, before this competition, nobody of us know any of the chemistry and biology knowledge about this program. The only stuff we're given are this GROMACS tutorial. And like, for example, let's go to the first one. Can you all still see my screen? This protein shaped stuff here?
Yes.
Okay. Yeah, basically we follow this tutorial, and you'll see there are a lot of it first tell you how to It first tell you how to set up it, but starting from the next page, you need to do some analysis on this proteins, and you have to note how different acronym stands for whatever words. For example, the NR is the atom number, and you sometimes in the I think in the question sheet they're using this acronym. So if you don't really understand this, you'll feel like,
I understand what the question prompt is also very challenging, because
the problem is super challenging.
It's very domain specific. It's not really meant to.
Yeah, it's basically like putting this protein into the solvent, like what different kind of solvent, and take out the crystallized water and whatever. If you don't really understand this, you'll find it super hard to even start. So yeah, I can remember it's super hard, but it's fun. And let's go back. Oh yeah, thank you, Zihao.
Yeah, no problem.
Is that all you want to talk about?
Yeah.
Sure. So let's go back to MEMXCT then. All right. So MEMXCT. Does anybody got any question? Tell me for now. If not, I'll just go to MEMXCT. Okay. I'll assume there's no problem. Let's go to MEMXCT. So unlike other applications, MEMXCT is not scored based on your performance. It's more, as Mary said, it's more about how you reproduce the experiment and how you explain the result. Why is it the same? Why does it differ? So, but the most important stuff for reproducing a application is first to understand what they're doing and what their algorithms are talking about. So let's see. For MEMXCT, you basically have a diagram called Synogram. So on the C part, you can see the Synogram is a diagram that you don't really understand what's going on inside. It is collected by using this setup. So in the middle is whatever. For example, in this one, I assume it's a brain. Uh, it's a part of the mouse brain. So what you do is you have an X-ray source. You shoot the source uh, through the mouse brain and using this detector to catch the projection. And while at the same time, you are in the middle, the part is going to rotate by itself, so that your detector is actually going to collect a set of images and putting them together. You got this diagram called Synogram. So this is basically uh, projections from 360 degrees all put together, and you have no idea what is inside and what's going on here. So what we really need is this final tomogram. It's more like a brain, it's a cut of brain, right? And maybe doctors or expert will know what's happening, or what disease this mouse got. So what we really need to do for this MEMXCT is go through this iterative reconstruction. So basically, you are still solving a linear system of equation, and you're looking for the best representation of the Synogram by doing a gradient descent. So traditionally, we are doing this iterative reconstruction one step by one step. So you'll realize that for each step, you probably will do some matrix inversion and a lot of computation. But for, let's say, for the first step, you do a lot of inversion. For the second step, you are still going to do the same matrix inversion, but you will not need the result from the first one. So basically, you are actually putting this job as a computationally very heavy one. So each step, you're only doing whatever the step required. But MEMXCT, its full name is memory-centric X-ray computed tomography. So it's called memory-centric, meaning that we're converting this computationally very heavy process into a memory-heavy process. But this so-called memory-heavy process can be resolved by adding more compute node as we have supercomputer. So basically, we are using supercomputers to solve a CT reconstruction problem. Okay, actually, I want to show you. Yeah, let's talk about this Hilbert curve. So as you can see, this. Let me use the original diagram, because this one, I feel like it's, yeah. So let's go to the, yeah. So as you can see, this diagram here, it shows the reading pattern of the Synogram and Tomogram footprint. So basically, assume this is your image. Your to read, as you can see, that we are collecting the data from rotation, right? So we are not actually going through a very regular reading pattern, like one by one as you access an array. You will read through this image by this curve footprint. And if you are familiar with computer architecture, you'll know that this footprint will not follow a regular data access pattern. So basically, you will not be benefit from data like from data locality, like you have in a C array. So the resolution for this, the solution for this is to have a decomposition algorithm using the pseudo Hilbert like curve. This is just a normal space filling curve, and as you can see, it actually decompose in 3 different levels. It first decompose the domain. So this is all the compute resources you have. You decompose it by assigning a different domain a number and you put it to the, let's say, put it to a different node or put it to a different node. And for each node, you then decompose it in a process level. It's actually quite similar. Like it's the same pattern. It's a Hilbert, pseudo Hilbert. It's a space Fellman curve pattern. And by doing this, we're not only let's see. So it's not. So then at the very end, you decompose it at a thread level. So each block stand for a subtask that is going to be solved by a thread, and this curve. Let me put it in a little bit. So by using this curve, we're ordering the blocks by the trace of the curve. For example, you can see from this one, this is 0, 1, 2, 3, 4, 5, 6. And inside, the indexing is also the same. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and blah, blah, blah. And you can see by using this pattern, sorry. Ooh. So by using this pattern, this access are more regular or less irregular than the original pattern we used. So by using the pseudo Hilbert curve ordering, we actually again benefit from the data locality, which speed up the data a lot. And another part I was talking about when I was talking about HPCG is a sparse matrix multiplication. And in MEMXCT, they also use a sparse matrix multiplication, and their way to solve it is by using two array to store using two, I would say, array or matrix to solve to solve the sparse matrix multiplication problem. So let's recall a sparse matrix or a sparse vector is a vector that consists of a lot of zero entries, and only a few of the other entries are non-zero entries, right? So instead of storing the whole matrix, what they try to do is they store the index. For example, given an array with length 100, only the second and the third like position, the location is the non-zero entries. So we, instead of saving this 100 lengths, this array of 100 lengths, 100 element long, we store the other two array, which called the index array and the value array. Each was 2 elements. So the first index array is going to store 2 and 3 because only the 2 and 3, index 2 and index 3 are non-zero. And the value array is going to store the value of the original the original sparse matrix at index 2. And what we are trying to do is when you want to see the non-zero entries, you first go to the index, and then you can use this index array to access the original sparse matrix. So by using this, although it's still computationally not like quite easy, but it's a more feasible way to solve sparse matrix multiplication. And this is, I believe, called a gathering operation in like computer architecture literature. So let's see. And putting that all aside, we are going to read a little bit about the experiment part. So basically,
Jacob,
sorry.
You have a question in the chat.
Oh. So question on XCT. Data given in terms of 2 variable. What do you mean by 2 variable? Sorry, I didn't quite get the question.
Lou, you can go ahead and ask it if you'd like,
Yeah.
but you're muted.
Just from when you started it in the first slide, so that's the results of the X-ray, right?
Wait a second.
So if you go back to the
Right?
XCP,
This one?
no, yeah, right. So your the experiment is that you're rotating that.
Mm-hmm.
By the way, this is a very not a very good figure. Is that from a paper? You see, you can't put a detector right along the path of the X-ray because all you get is a burnt hole. So the detection are usually angled. So then you rotate, so the experiment's rotating so that's a theta. Then since you have a two-dimensional curve with functions, so you have two variables, right? What is the other one?
Okay, so the data given is actually a collected Synogram. So we are not given all this scanned data, but this one single Synogram. It's an image. It's a binary file, actually.
Yeah, I see. So yes, I'm beginning to figure out later on the slides, the next slides, the figure 5, they are just 0 and 1s, is it?
Yeah.
So so we got theta, and then what was rho?
Rho is you can think of it as a dimension. Like it's not a, so the or do you mean the p theta? It's actually the projection, stands for projection, and the theta is the index.
Sorry, theta is the rotational.
Yeah. Theta is the rotational, like.
What is rho? Or you got it p? I think it looks like rho.
Okay. The rho is like the projection, the image you got at that angle.
Oh, I see.
Yeah. So basically.
So when they talk about tomography, you're getting layers of this, or just one?
We are only getting one.
Oh, the Synogram is only one.
Yeah.
Layer.
The Synogram is only one.
I see.
And yeah.
So what does the final tomogram mean?
So you can see the Synogram is a scanned image, right?
Yeah.
And let me show you some example. So let me show the whole screen. So now let's see. Given these are the data given at the competition. So for example, for this one, this is a Synogram image. The data given is not an image. It is computed by another like algorithm. So basically, this image doesn't represent anything, right? We don't really know anything from this diagram. What this algorithm is trying to do is to reconstruct the original 3D, not 3D, like the original image, which we call as a tomogram, at last. So the result for this one is this reconstruction. So you can see this is a shell rock.
Mm-hmm.
Yeah, basically we are converting this diagram into this one. And this process traditionally eat out a lot of computational resources.
So yeah, so what you're doing is you have a big matrix and you transform it into another matrix.
Yeah. Basically, you are trying to solve the least square problem.
It's always two-dimensional.
Yeah. And this and what's super interesting is that this paper is the 2019 best paper. Mm-hmm. And 2020, one of the 2020 best paper is from the same author, but this application on the 3D reconstruction.
I see.
So this one is only for 2D, but I'm not sure if it's going to be the 3D reconstruction this year.
Yeah.
So yeah.
And can you send us the reference? I saw
Okay.
a little bit at the top. It says SDSC something, but
you mean this one, CDS one?
can you send us a reference?
Reference to the paper, or do you mean a reference to the paper?
Yeah, that's what he's looking for.
Yeah,
Okay, that's probably good enough. I can search that if I get this. Yeah,
I'll put it in the chat.
that's fine. That's good enough. I can. That's enough information. So many authors.
Yeah, a lot.
Okay. Yeah. Thank you.
No problem. And yeah, and we'll actually keep talking about this. Yeah, you can see from this part that they're saying that we are actually solving this square problem. And yeah, and each step is divided in A is a forward model, R is a regularization, and C is a constraint. And yeah, basically we're solving this this problem.
Yeah, for layers of it. Yeah, it's tomography. So
yeah, and we're doing a gradient descent, and this gradient descent is very computationally
challenging, intensive.
Yeah, yeah, intensity. So what this MEMXCT is doing is by it's more like a dynamical programming approach, but it's not actually using dynamic approach. It's like it saves the on the fly computation at each step of gradient descent. It saves it, and once it needed in the future, it can retrieve from the history, so that it's actually memory centric, like solving this problem. But you know, a computationally inefficient problem is like consuming more times, right? But we can't really buy times, but we can buy more memories. So we can actually have a very huge computer. As you can see, let me show you a very like this result scared me. So when they're doing the strong scaling result, they're using 400 nodes for this data set. And I believe RDS2 is the mouse brain. Let me just double check. Yeah, RDS2. Yeah, it's a mouse brain, and it's regular. It's like so as I mentioned, we are saving the on-the-fly calculation, right? So after saving all those calculations, we will have a runtime memory of 5.1 terabytes.
Yes.
Which can really be used in a hospital or whatever place, but a supercomputer center. And I'm not even sure if our center got 4,000 nodes to compute. So it's a fantastic result, and it's actually quite interesting. And what I want to show you is some of the optimization strategy I used to further speed up this MEMXCT. And let's have a look at the code or my compile code. So this is my code for, let's not see this one. Let's go to a performance one. So this is an compile code I had for compiling the program. And so yeah, let me first talk about which part of the experiments are we reproducing. So for this one, they're performing their so-called one node or single device performance on the Knight's Landing, the KML, and their performance on ADS1, which is a very small file, is like we are only talking about the gray bar, because the gray bar is with all the optimization strategy I mentioned before, like using the space filling curve indexing and using the sparse matrix multiplication kernel, and also with some buffering system called multi-stage buffering, where you put locally closed data into the same L3 cache and then make the other part like into the L2 cache, so that you can still benefit from the data locality. And basically we're trying to reproduce this pattern. And although we're given some different data, what I want to show you is that my reproduce the result for ADS1, ADS2, ADS3, and ADS4. So here is it. As you can see, these are my results. And it's like with different strategy, but the problem is I didn't use the optimized strategy here, but we can look at the blue bar, and you can see that I didn't reach. So they're having 80 something and then 100 something, right? So for ADS1, ADS2, which are very small result, I have only like 60 and 40 something. But for ADS3, ADS4, I'm actually having a similar, even better result than theirs. So during the competition, we are actually required to explain why is this happening. So why do we have ADS1, ADS2 lower, like having a lower G flops and their result, while our on larger data set ADS3, ADS4 we have higher G flops. So the reason turns out to be the machine they're using got an MCD RAM, so which is this one, which is 16 gigabytes, and their machine itself cannot compute as fast as an HP 120 instance, as I mentioned before. What this RAM can do is that MCD RAM can do is that ADS1 and ADS2 are small enough so that it can be fit completely into this RAM, while we don't have such a big RAM. So we don't really have ADS1, ADS2 fit into the RAM directly completely. So we have a slower result. But for larger data, for ADS3 and ADS4, it's too large to be fit into the MCD RAM, because I believe this ADS4 requires 120 gigabytes of memory, runtime memory, and the MCD RAM is too small. So basically, our machine, the HP 120, is strong enough so that we actually have a better performance than KNL. And this is the first one we need to reproduce. And the second one we need to reproduce is the memory bandwidth utilization. This is, I'm not going to show the result here because it's kind of, actually I'll show the result. Let's see. So basically the bandwidth. So I'm not using the same data, but you can see that it's basically, I can't say anything because I can't remember the theoretical peak of HP 120, but basically we're matching their data on a similar size task input. And another very important part is this strong scaling, as you can see. So let me introduce you a little bit more about this curve. So this blue curve is the total time used, and x-axis is the number of nodes, while y-axis is the solution time. The whole grid is log scaled, and we can see that this blue curve is going down, but at the very end a little bit up. And this red part, this red is the, let me recall. This A part should be the what was it? They should mention it on the top. I can't remember. Yeah. Okay, so this AP is multiplication cost. and the C is a communication cost, and R is a reduction cost. Okay, that's good. Let's go back to the experiment. So as the nodes increase, the multiplication time decreased. It's in a super linear. So this black line here is the benchmark. It's O1 over P. So if we go through this line, it's a linear speed up. This red line go through a super linear speed up. While this yellow line, the C, is a communication time, which is reasonable since we have more nodes. The communication time kind of increased, while the reduction time, this purple line, stay at the very bottom. It doesn't change a lot. So let's see. This is on RDS2, but we don't have such a huge data. It requires 5.1 terabytes and using 4,000 nodes. So what we actually doing is working on. Let's go back to the. Yeah, let's show some cool result. So let's see. So let's have a look at the CPU official. This is not a good one. I don't think so. Okay, yeah, let's have a look at this one. So this is a strong scaling diagram I have. And you can see, although at the very beginning, this total time is, this red multiplication time is dropping, it actually dropping a much slower rate than the original one, because in the original one we were talking about, this red line should be having a super linear speed up, right? The reason for this is that CDS2 is so small. So once we increase it from 1 to 2, we actually reach the diminishing return. So even if you try to add more of the more nodes, it doesn't really help the total time. Even worse, this C and R are reduction time and communication time. As the nodes increase, the purple line, the yellow line gradually dominate the time spending. So actually spending much more time than we expected. So the total time didn't actually go down. So even if you didn't see the exact same result, you need to explain why. You need to find a reason. So for the, let's see, do I have a better diagram? Yeah, I think this one is yeah. So for this one, I use the optimize. It's kind of like cheating, but I'll explain why. So basically, in this diagram, you see a very good result. Like blue line go down at the very beginning and then go up a little bit. The red line is experience a super linear or approximately linear speed up. Sorry. The yellow line is going up. The communication time and reduction time remains at the bottom. So why do I say it's like cheating? So when they're talking about measuring performance, they're calling it a single device performance. But what I was trying to do is I was doing a single socket performance so that I can actually map different. Yeah, let's go back to the code to explain a little bit more. Yeah, you can see remember for HP 120 instance, there's 60 CPUs on a socket, and there are 2 sockets on the board. So if I'm only using 1 socket, I'm dividing the 60 CPU into 4 groups, because each 15 CPUs share the same L3 cache. If I can map the task that's close to each other on the same L3 cache, then there should be a pretty good performance. So as you can see here, but if you've learned MPI, you now know that number of processes is 15, but we are actually using 4 open NumPy threads. So we have 15 ranks and 4 threads. So in total, there are 60 what process or 60 threads? Yeah, 60 threads. And we use this map by L3 cache so that processing element is the L3 cache, and we are using 4 of the L3 cache. So each 15 tasks is mapped to the same job. And you can see the Slurm script, they're per node is 15 and CPUs per task is 4. So in this case, we used the one single socket. We get a very good result, as you can see. It's quite similar to this one. So let's have a look at the chat. Oh, okay. So after this going, I'm just gonna show you some more result from the beside the result. You can see that for doing all these experiments, I will have to run it a lot of time. So you have to have the scripts. So these are my scripts. And let me show you the result, output result. So for, let's say, CDS1, you can see I've run experiments hundreds of times. And by doing that, I can take average and get a more like credible result. So you actually need to submit all of these files to the organization, or yeah, basically. So yeah, that's all I want to talk about. But I hope this doesn't scare you, because although it's hard, but we really have enough time for SC21, and it's really a fun experience. It's even better when you start when you recall it. So we're not only looking for team members, we're also looking for whoever interested in mentoring it, because you can see that although I spent a lot of time on this application, I still didn't catch the mistakes, or I still didn't get 100% like about the setup, as Lou pointed out, because I'm not a physics major, and reconstruction and X-ray are somehow too hard for me. But we are always prepared as computer scientists to solve problems from different domains. So we are really welcoming people from different domains as well, because probably you're like, for example, if you're a biology people and we have you last year, then probably GROMACS won't be a tough problem to solve. So yeah, I'd welcome anyone to apply, both for the team members, and also if you're interested in helping, I would like to have you as one of the mentors, because probably I'll be the mentor for the team this year, and yeah, just to look for more members. Yeah, thank you.
Thank you, Jacob. That was very good.
I
Obviously,
didn't take too long. Sorry.
go ahead. No, you didn't take too long.
Yeah, nah, I'm just saying that I hope it didn't take too long.
No. I think what's amazing is how much the students learned, given that we had very little time last year. So we started HPC user training around the 1st of August, and by November, they had all come up to an incredibly high skill level, and working as a team and helping each other and working with mentors. And we never know what the applications will be. And so then we start reaching out and finding mentors to help us just understand the physics. I have a physics background, but MEM XCT was not so much about the physics, it was about some advanced computer science memory management. So it was very interesting. Anyway, excuse me. I think that's it, unless I'm going to stop recording.